Hi everyone, my name is Chai. Today I will present my paper for the EMBC 2021, which is titled Deep Reinforcement Learning with Gait Mode Specification for Quadrupedal Trot-Gallop Energetic Analysis. The table of content is as follows. I will start by an introduction and motivation of DRL Gait Mode Specification. Then I will talk about the methods used in this paper, followed by the experiments conducted in this paper. There are in total 3 experiments in our research. And finally, we'll end the presentation with a conclusion. We'll start by the introduction and the motivation. And so the common themes of quadruped researchers are to study the relationship between the gait types of the quadruped, the forward speed of the quadruped, and also its energy efficiency. And examples of quadrupedal researchers are, for example, the study of gait transition at different speed. For example, in this study, the author shows that at lower speed, the trot gait, for example, is better, and at higher speed, the gallop gait is more energy efficient. And researchers often use CPG for gait generation in a quadruped robot in their experiments. So, but however, recently, more and more researchers make use of DRL in quadrupedal researchers. For example, in this study, we have an example of a DRL learn gait planning experiments. And the reasons that researchers use DRL more and more often is that there are some upsides, such as the DRL is adaptive to different settings of a quadruped robots, and also it requires minimal manual tuning. And however, there are also some downsides, which is it requires a long training time, and the gait types are also random after training. So this is not good for quadrupedal researchers. The objective of this paper are as follows. We want to propose a gait mode specification method to generate deterministic gait type after training. We would also like to promote faster learning convergence through our method. And we would also like to demonstrate through experiments the possibility to carry out similar gait studies, usually done using classical controllers, but this time we are going to use DRL-generated gaits. Finally, we would also like to demonstrate the advantage of DRL through the exploitation of passive joint spring effect in our quadrupedal agents. And the methods used in this chapter is again the use of a DRL algorithm, or more specifically the SAC algorithm. And then we'll use a simulated quadruped agent, which is shown here. And the reward function used for this agent is to run at a given target speed. But at the same time, we want it to consider its energy consumption as well. So we add another term here. The gait mode specification method proposed in this chapter can be illustrated in this diagram. So here the DRL policy will output the input torque for the right limbs only. Then for the left limbs, when the gallop mode is specified, the input torque for the left limbs will be equal to the input torque of the right limbs, so that the left and right limbs move in phase and it can achieve the gallop motion in this way. And when the trot mode is specified, the input torque for the left limbs is the negative of the input torque of the right limbs, so that the left and right limbs move in opposite phase to achieve the trot gait. And then these two torque are concatenated and given to the quadruped agent, and this is repeated throughout the DRL learning process. The evaluation metrics used in this chapter is the performance metric, which is the distance covered by the half theta by the quadruped agent during a certain duration. And then the second metric is the energy index metric, which is the energy consumed by the quadruped agent during the running course. And hence now we will present the results for the 3 experiments. And first we will show the effects of the DRL gait specification. So in this video, we can see that when the gait mode is specified, we have indeed a certain gait type. For example, when gallop mode is specified, the left and right limbs move in phase, and for the trot gait, the left and the right limbs move in opposite phase. If you look at the performance plot, we can indeed see that when the gait mode is specified, the learning rate converge, the learning processes converge much faster than the case without any specification. Hence, we have indeed sped up the learning speed. And now we'll conduct an energetic study between the different gaits. And so we'll let the quadruped agent to run at a speed of 3 and a speed of 5. And the questions that we are trying to answer is that, does in lower speed, the trot gait is better than gallop gait? And when higher speed, is the gallop gait better than the trot gait? Which is the result shown in the previous work. And if you look at the performance plot, we can see that at higher speed, which is the speed of 5, the gallop gait is indeed better than the trot gait. And at lower speed of 3, the trot gait, which is the blue curve, is indeed better than the gallop gait. Hence, we have indeed achieved a similar result with the previous work. So this is interesting because DRL-generated gaits can also be used in an energetic study. And finally, we'll show the advantage of DRL through the experiment of exploitation of passive joint spring effect. So what is the passive joint spring effect? So it has been shown in a quadruped that there's a very efficient transfer of kinetic energy to elastic energy during the running motions. And this is thanks to the passive joint spring effect between the joints of the quadruped agent. And so it is common for researchers to model the limbs of a quadruped using two springs between the joints. So in this experiment, indeed, we would like to modify the passive joint spring effect in the quadruped agent. We'll modify from a minimum joint spring setting to the default setting, and then to the maximum setting. And then we would like to know whether the more spring effect the agent has, is it running more energy efficiently? This is the question that we are trying to answer. And now let's look at the result. So on the left side, we can see that indeed when the passive joint spring effect increases, the performance also increases. However, what's more interesting is that in terms of the energy plot on the right, at certain point of time, the energy consumption for the 3 different settings consume exactly the same amount of energy. However, as the learning progresses, the DRL algorithm somehow found a way to exploit the passive joint spring effect in the quadruped agent. And finally, the more joint spring effect the agent has, the less energy is consumed during the running course. So we have indeed shown that the DRL algorithm has this advantage of exploiting the dynamics condition of the quadruped agent. The conclusion of this paper are: the proposed gait mode specification method has successfully sped up the training convergence by reducing the redundant solution space. We have also successfully imposed a certain gait type at the output. Secondly, we have also demonstrated through our experiments that DRL could be an alternative method for quadrupedal gait generation for energetics analysis. And finally, we have also demonstrated the adaptation ability of DRL policy through the passive joint spring exploitation experiment. So this is the end of my presentation. Thank you for your attention.